We are continuing on in Chapter 8. This is our second set of notes, and we are still talking about similarity, and we're going to focus on similar triangles. So the first thing we want to discuss is ways that we can prove or know ahead of time whether or not triangles are in fact similar, and then use what we know about similar triangles to solve problems. So the first way that we can prove triangles are similar is if all of their corresponding angles are congruent. So if A was congruent to D, angle A was congruent to angle D, angle B was congruent to angle E, and angle C was congruent to angle F, I could say that triangle ABC is congruent to triangle DEF. Sorry, not congruent, similar. That little squiggly means similar to triangle DEF. The next way is side, 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 but it is not like when we were proving triangles congruent, because it's not that we have congruent sides, it's that the ratio of the corresponding sides for all three sides of the triangle is the same. So let's call these sides length A, B, C, and D, E, F. So if the ratio of A to D was equivalent to the ratio of B to E, and is equivalent to the ratio of C to F, then triangle ABC is similar to triangle DEF. Again, that little squiggle means similar. Okay, so that's our second method, and our third and final method is side angle side, and this is when we have two corresponding sides that have equivalent ratios, and the angle in between them is congruent. So if angle B were congruent to angle E, and let's call these sides A, B, and D, and E. So if A over D, that ratio, was congruent to B over E, and that angle that's in between them is congruent, the corresponding angle in between them, then triangle ABC is similar to triangle DEF. Now again, it has to be the angle that's in between the sides that have equal ratios. So the corresponding sides with equal ratios, the angle must be in between. If it was a different angle, we could not verify that these were similar triangles without more information. Alright, so we're going to use this to solve a couple quick problems. Let me scoot my page up. So starting with number 1, the sides of one triangle are 8, 14, and 12. So I'm going to draw this triangle, and because I'm not specifically told what side is what, I'm going to order them from smallest to largest. So 8, 12, 14. And then the sides of another triangle are 18, 21, and 12. And so again, I'm going to number them from smallest to largest. So that's going to be 12, 18, and 21. I apologize for that bell. So if I want to prove that these triangles are congruent, there's only one method I'm going to be able to use, and that's side, 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 because I don't know anything about the angles of these triangles. So side, side, side means that the ratio of each corresponding side has to be the same. So let's verify that. So our smaller two sides would correspond, so that ratio 8 to 12 is equivalent to 2 to 3 if I simplify. Okay, so then my second largest sides would correspond, so 12 over 18, that also simplifies to 2 over 3. And lastly, my two largest sides, 14 to 21, that also reduces to 2 to 3. So the ratio for all of the corresponding sides are equal, so I can prove that these are similar triangles by side, side, side. Now number 2, I'm told that EA is perpendicular to LP, so I'm going to indicate that with my right angle symbol. N is the midpoint of LP, so if N is the midpoint of LP, that means that LN is congruent to PN. And lastly, I'm told that P and R trisect segment EA. So P and R trisect, which means it divides it into 3 equal parts. So these 3 segments are congruent. And I want to prove that triangle PEN is similar to triangle PAL. And I'm going to do this, I'm not going to use a formal proof, I'm just going to use what we know about ways that we can prove triangles are similar and talk through it and make some notes. So, based on this information we're given, I can already tell that the only way I can prove that these are similar is by the side angle side method, because I only know about two sides and one angle. And the angle I do know about is in between the two sides that we would have to prove that the ratio of those sides are congruent. So first of all, if this is perpendicular, that means both of these angles are right angles. So that angle LPE is congruent to angle LPA because all right angles are congruent. So there's my angle. Now I need to focus on the two sides. So because LN and PN are congruent, PL or LP, however you want to say it, this segment we know is twice as long as PN because it's twice of the same measure. So this ratio of LP to PN would be 2 to 1 because it's twice of the same length of the segment. And then if we look at our horizontal pieces down here, again, we have these congruent segments, so the ratio of PA to EP is also going to be 2 to 1 because I've got these congruent segments. There's 1 for EP and 2 on PA. 2 to 1. So I've got those two congruent, two equal ratios for my corresponding sides, and the angle in between them are congruent. So therefore, these two triangles are similar by side angle side. Right, and I'm going to flip over to our next page. We are going to move on now to section 8.4. And that is that we are going to use what we know about similar triangles to solve some problems. So remember, what we know about similar polygons is that our corresponding sides are proportional and our corresponding angles are congruent. So starting with this first example here, Mr. Bunny is 9 feet away from a flagpole that is 15 feet high. So I'm going to draw. We've got a little bunny here, and we've got our flag, and it says he is 9 feet away. So this distance from here to here is 9 feet, and the flagpole is 15 feet high. So we've got 9 feet and 15 feet. If Mr. Bunny's shadow is 2.5 feet long and touches the end of the shadow of the flagpole, how tall is the bunny? So if Mr. Bunny casts a shadow here, and our flagpole also casts a shadow, and their ends touch each other, and we know this distance from here to the bunny is 2.5 feet. We want to find how tall the bunny is. So I want to know this height here. Let's call it X. So if I were to draw a segment from the top of the flagpole to the end of the shadow here, I can form a triangle. Now, if I want to use what I know about similar triangles, I can solve for X by using my equal proportions. So or ratio. So the ratio of the height of the flagpole to the height of the bunny would be equal to the length of the flagpole shadow to the length of the bunny's shadow. Now what's important to note here is that the length of the flagpole shadow is going to go all the way, the 9 feet and the 2.5 feet. So this length of the flagpole shadow is the sum of those two, which is 11.5. So the shadow of the flagpole is 11.5 feet, and the shadow of the bunny is 2.5 feet. So now I have my proportions set up, and we can use our cross multiplying to solve for X. So 11.5x is equal to 15 times 2.5 is 37.5. And if I divide both sides by 11.5, I get that X is approximately 3.26 feet. So that's how tall my bunny is. Alright, and then number 2, Lance the alien is 5 feet tall and his shadow is 8 feet long. At the same time of day, a tree casts a shadow that is 32 feet long. How tall is the tree? So again, I've got triangles, and I'm going to use assumptions that they're similar to solve for the height of this tree. Let's call it y. So I'm going to set up a proportion. So if these are similar triangles, the ratio of the height of the alien to the height of the tree would be equal to the length of the alien shadow to the length of the tree's shadow. So I'm going to use my cross multiplication again, and I'll get that 8y is equal to 160. Divide both sides by 8, and I get that the height of my tree is 20 feet. Last one for this page. We're using the information in the diagram to find the height. So everything in this diagram is going to help me determine the height of the tree. So I've got the height of my building here is 160. This height of my tree right here is what I'd like to know. Let's label it as x. And then if you look, I've got tick marks to indicate congruent segments. So these two segments are congruent, and if this one's 144, this one is also 144. And then my two at the bottom are also congruent. So if this one's 120, this one is also 120. So I need to set up a proportion to solve for x. So the height of the building to the height of the tree, that ratio should be equal to, now there's two ways you can do this. You could use the length from the building to the edge, and then from the edge to the tree, or you could use the hypotenuse of both of those triangles. Either way is acceptable. I'm just going to go with the bottom one. So the height of the building to the height of the tree to the base of our larger triangle to the base of our smaller triangle. So the base of the larger triangle is 120 and 120, which is where the 240 came from. So again, I'm going to use cross multiplication. So 240x is equal to, it's a pretty big number. And if I divide both sides by 240, I find that the height of my tree is 80 feet. All right, and we just got two more problems to work. So I'm just going to skip ahead to number 5 on our last page. So we have this set up, we have our values. We know that she's 5 feet tall, 12 feet away from the mirror. The mirror is 48 feet away from the flagpole. We want to find the height of the flagpole, so let's call this y. So I'm going to set up my proportion. So the height of Michelle to the height of the flagpole should be equivalent to the distance that Michelle is from the mirror to the distance that the flagpole is from the mirror. So again, cross multiply, and we get that the height of the flagpole is 20 feet.